afternoon. My name is Kate Woloshin, and I'm a program specialist with Alberta EcoTrust's ENBIX initiative. Thank you all for attending today. This is the third presentation in the Residential Building Technology series hosted by ENBIX and SSRIA. Today's session will be about the considerations for window design and installation. We're going to take a moment to introduce ENBIX and SSRIA before moving into the main part of our program. As we carry out our work across Alberta, we commit to respecting and upholding the values and traditions of the Indigenous communities who have lived and continue to live here. Alberta EcoTrust Foundation operates across all Alberta, so we recognize that the traditional territory of many diverse Indigenous peoples. This includes Treaty 6, Treaty 7, and Treaty 8 nations, the Blackfoot Confederacy, comprising of Siksika, Kainai, Piikani First Nations, the Cree, Dene, Nakota Sioux, Saulteaux, and the Métis nations of Alberta. These lands who have been stewarded by Indigenous people for millennia, who have maintained a deep connection to this land and its resources. We honor their histories, language, and cultures, and continue to recognize the significant contributions they have made and continue to make in this region. Alberta EcoTrust Foundation is a charity that leads and supports environmental and climate action across Alberta. With over 30 years of experience, we deliver programs, grants, initiatives, and strategic engagement to help create a healthier environment for all Albertans. We've been a long-standing source of funding, training, and skill building for Alberta's environmental community. In recent years, AEF has expanded into direct program delivery with a growing focus on reducing the environmental impacts of the built environment. Alberta EcoTrust has two programs that support the building industry, ENBIX, which stands for the Emissions Neutral Building Information Exchange, and the Alberta EcoTrust Retrofit Accelerator. ENBIX is a collaborative initiative of Alberta EcoTrust that brings the building industry together to share knowledge, build capacity, and support building and renovation practices across Alberta. The goal of ENBIX is to reduce emissions from new and existing buildings. We do this by hosting events, sharing resources, and developing and strengthening the skills of people and organizations through training, peer-to-peer learning, and communities of practice. Alberta EcoTrust Retrofit Accelerator is a free coaching program designed to guide building owners and managers through sustainable building upgrades known as deep retrofits. These take on a whole building approach to standard upgrades to reduce emissions, energy consumption, and operating costs. And the Smart Sustainable Resilient Infrastructure Association is a not-for-profit industry association that fosters collaboration and action to accelerate the adoption of innovative, low-carbon technologies for the built environment. SSRIA is aligned with the many government and corporate targets of reaching net zero emissions by 2050. SSRIA achieves their mission by facilitating collaboration amongst all building stakeholders, supports the growth of businesses developing innovative low-carbon solutions, funding demonstration projects, and gathering all the learnings and data from those projects to create a knowledge hub. We're going to run a quick Zoom poll to get a better idea of who's in our audience today. And today's speaker is Darrell Paul, a seasoned building envelope consultant in Alberta with over 45 years of experience in the construction industry. He began as a framing carpenter and worked his way up to site supervisor, construction manager, and marketing manager, earning PHBI's Master Home Builder and Master Home Renovator certifications in 1997. His practical expertise is showcased in the building envelope tie-in details. Darrell founded Qualistat Building Performance Consultants in 1986, offering design and testing services to builders and warranty providers. As an instructor with CIET, PHBI, and SAIT, he shares his passion for building science and performance-based construction in many ways. He holds certifications including Residential Air System Design, Level 2 Thermography, and Certified Energy Advisor. Committed to ongoing learning and industry advancement, Darrell regularly presents at seminars such as this and contributes to committees such as CSA A440 and the Canada Codes Joint Task Group on High-Performance Homes. He also supports course development with PHBI and Fenestration Canada. I'll turn it over to Darrell for his presentation now.
Darrell, you're muted.
There we go. Sorry. Can everybody see that okay?
It's your full view.
There we go.
There we
Okay,
go.
good. All good. All right. So welcome everybody. Nice to see everybody, sort of virtually. Um, we're going to talk about windows today, window designs. We'll talk a little bit about design and the design aspect, dealing with solar heat gain and U values. And then we'll spend some time on installation of windows because, you know, those two combinations are very important when it comes to the windows themselves. So windows have been in the news a lot recently, especially after the heat dome events a few years ago in BC. There was over 600 people that died from the heat dome because they just couldn't get out of the heat. So that precipitated some changes in the building code, which were called peak cooling loads. And we'll touch on those a little bit in a minute. But basically what it means is a lot of our windows are too hot in the summertime, and then they're too cold in the wintertime. So when we get those kind of factors going on, it makes the house very uncomfortable, and we need to look at ways to improve our designs and increase the efficiency of the window so that the comfort level goes up. But then we also need to reduce the callbacks on, you know, rework, damage, leaks, things like that. Traditionally, in my background, started as a framer and then a site supervisor, a lot of the windows were installed as an afterthought. You know, the framer was required to put the window in. He didn't really get a lot of direction on how to install the window. The window was just kind of put in place, and then everybody worked around it. So it's not until recently with the energy code changes that we've started to make, you know, positive inroads in how we view windows and how we look at windows. Part of the issue too is when we look at the installation of windows, like when you look at these images here and you see some of the deterioration, some of it is on older product, like in the bottom center, you see that, you know, that's a plywood wall. And you see the weakest area is usually at the bottom of the wall, but even the different ways that materials perform. So you look at the center picture here and you look at the tar paper that's completely worn out on the wall because there's been such a volume of water that has run down the side of that window, off the flange and onto the OSB, that it's even deteriorated the tar paper. So, you know, we think of tar paper as a relatively robust product, but not always if it's exposed to water for long term. So we want to look at the design issues, we want to look at the installation issues, and one of the best ways to do that is to start by looking at the history of the windows. You know, if you go back a number of years, you know, these windows that you see in the illustration here would probably be windows from the, you know, 1920s, 1930s, 1940s, before we started using insulated glass units or the sealed units that we typically see today. But when you look at these old windows, why are they still in such good shape? If you ever run out to the East Coast or the West Coast, you'll see windows that have been exposed to a lot of weather, a lot of rain, and a lot of moisture. And yet they still seem to be in pretty good condition. And why is that? Well, there's a number of factors. The two biggest factors is the high air leakage that you see around the windows. So there's nothing trapped. They're vapor open and they're air open. So when they get wet, they dry quite rapidly. And there's a lot of heat loss because of the low insulation value. And what does it take to evaporate and get rid of water? Well, it takes heat and air. So if you've ever thrown your clothes into the dryer and turned them on air only, or some blue jeans, hung them out on the line when it's really humid out, you know that it takes a long time to dry out the moisture if you don't have the heat involved. So those are two main factors. So as we put more insulation in the wall and we put more air tightness into our assembly, we lose the ability to get rid of the moisture. The other factor here is when we look at the growth, the old growth fir that was used in a lot of these lumbers, right? They're clear fir. There's not a lot of knots. It's pretty solid. And as it gets older, it gets more solid and more resistant to moisture. So these materials performed really, really well. So those combination of things, you know, provided good performance. However, when you look at the design of the window and you look at the fact that most of them were single pane, Most of them were very cold in the wintertime, very frosty in the wintertime. A lot of times you would have to add storm windows to give it that extra protection to keep it just, from having too much draft. But then in the summertime, you had a lot of sunlight that came through the glass and you produced a lot of heat buildup in rooms where there was a lot of windows. So you didn't really have much control over the environment, whether it was from, moisture or from heat or cold. So modern windows have been designed to kind of look at those components and look at how they can be, reduced and how the comfort can be improved. So if we look at how windows work, how are they designed? Well, a window is designed so that it can deal with three forms of heat and heat energy transfer. So we've got them in three categories here. We've got on the left, we've got heat energy transfer, we've got control mechanisms, and then we've got the systems that we use in terms of the unit, window unit itself. So if you go to the top, we've got listed radiation. Well, how does heat transfer work with radiation? Well, it's a heat transfer through an invisible infrared energy. And if you think of using an infrared camera, when you use an infrared camera, it picks up highly emissive materials, like anything dark, anything rough surfaced, which can absorb heat and then re-emit that heat. That's radiation that's being transferred, and the camera sees that quite easily. It does not see low emissivity. It's almost invisible to an infrared camera. So that's what causes the heat, because the heat comes through, it reaches the surface, it's absorbed, and then it re-radiates that heat back outward. Now, the control mechanism is we either got to reflect that heat by using coatings, or we block the sun by shading. So that's the system itself. So on the system side, we either put a low-E coating on it or we put shading on it to block the sun. We could do that with, vegetation. We can do that with overhangs on the roof. We could put shading components on the exterior, but that's how we deal with radiation. Number two is we deal with convective heating. That's a heat transfer. So that's how we transfer heat through a fluid. It absorbs on one side and then the fluid gets warmer. It starts to rise. The cooler side falls and we get this circular convection that's going on within the material. So, with air between the glazing of an insulated glass unit, we get the movement of energy that way. Now, when the control mechanisms are used, we can either trap that air and compartmentalize it, or we can use a denser air. If you think of a window frame, a vinyl window frame, and you cut a cross section of it, you'll see all sorts of little compartments or openings which are sealed so that the air can't transfer. So then the convective looping occurs in one, and it's not directly connected from the warm side on the inside to the cold side on the outside. And then as the convective is happening in each individual component, it doesn't transfer heat as fast through. And then that's where we get the systems: convection sealed units, either double or triple pane glazing, and compartmentalized, such as in vinyl windows or fiberglass windows. The third one is conduction, heat transfer through materials. So when we transfer heat through a material, it's a direct contact and it moves heat through. So if you think of a piece of steel, it not only transfers the heat through, and it's a complete thermal bridge, or a piece of aluminum, but it moves it through very rapidly. So a steel frame window would not perform very good. It transfers heat so fast through there, and it has no ability to resist the heat flow. So when we look at the control mechanisms, then we want to slow the heat transfer through the solid materials by using a material that will slowly conduct the heat. So in our systems, then we use thermal breaks. We put a piece of rubber. So for instance, if we're doing an aluminum frame window, we'll have a thermally broken aluminum window because the aluminum on the outside doesn't touch the aluminum on the inside. We have little rubber thermal breaks. Or we'll use a vinyl window or a wood window frame, because those will transfer heat slower through those materials than it would through more solid materials like aluminum or steel. So that's the basic design factors that we would consider when we're designing a window. Now, in practical application, how does that work? Well, on the left here, you have a window label, and that window label gives you some very important information, which helps us to understand the performance characteristics of this particular window. So first of all, you have what we call the Energy Star label here. So, if you're using an Energy Star window, there's certain criteria for that Energy Star window, depending on the climate zone that you live in. And you would pick a window that Energy Star says is acceptable for that climate zone. So that just gives you a specific range of materials that you could use in a specific climate zone. But more specific, when we get into the performance rating aspects of it, we have several things. So first of all, the insulation value of that window. Here we have a window that's got a U factor or a U value of 1.19. Now, if you look at R value up here, the imperial R value, if we add an SI after the R, that tells us that it's a R metric value. So it's RSI. And the factor for converting back and forth is 5.678. So if you know what your R value is and you convert it by multiplying or dividing by 5.78, you can convert between RSI and R value. Well, U values are the same. And unfortunately, we don't list U values to make it easy to understand. So a U value would be down here at 0.21 would be the imperial U value, but a USI value or the metric value here at 1.19 would be the insulation value. So you don't want to confuse the two. And the easiest way to know this is that you're going to have a low number, usually below 2.0, which is going to be a metric value. If you get down to a 0.21 and it's a metric value, that is an unrealistically perfect window because that's about an R20. So you get used to those numbers after a while, but those are the U factors. And the U factors are important on the shady side of the house where you don't get sun, because that's the insulation value. It's also important nighttime. And things that can affect the U value are some of the coatings that go onto the window, but also things like argon gas, making the gas layer between the glazing, making that air denser. So it slows the convective looping or transfer of energy. So when we're looking at windows at 1.19, that's a reasonably good window, for a climate zone in zone 6, 7, somewhere in that area. When you get down into a 0.75, that's a fantastic window. That's going to be a triple glaze window. When you get up to a 1.8, 1.9, or even 2.0, that's probably more of a commercial window, thermally broken window. It's probably something you'd see maybe in a residential patio door. So we don't often use the U factor for imperial. So down here at the 21, we would probably just tend to ignore that. But it's amazing how many window companies will send out their details and they will include the imperial value instead of the metric value. So you just have to do that conversion. The second important one down here is solar heat gain. So the solar heat gain, when you look at solar heat gain, that is one of the more important values on a window. And the reason is because when the sun hits a window, how much of that solar radiation is going to get through, how much of it is going to heat the glass in the frame, and how much is it going to heat the materials inside of the house and cause the building to overheat. So if you have a high solar heat gain, you're looking in, numbers of around 0.7, 0.6. Those are high solar heat gain numbers. So the higher the number, the hotter that it's going to be. So if you had a 0.7 solar heat gain window in your house and it was winter time and it's very cold outside, you're going to get lots of nice free heat from that. But guess what happens in the summertime? If that's a 0.7 window and the sun is shining through there, you are going to cook in that room. So that's maybe not the best window to have there unless you can throw a shading device on it, or you have a tree that grows outside your window that gets lots of leaves on it in the summertime, and then they fall off in the wintertime. So you can control it either with, low emissivity coatings, or you can control it with shading, one or the other. Conversely, if you're looking at windows that are down in the 0.2 range for solar heat gain, those are going to give you really good protection in the summertime. You're not going to get a lot of heat, but you're also going to lose out on the free heat that's available from the sun in the wintertime. So if you have a larger percentage of glass on your house, then you're not going to get any of that free heat. The house is going to remain cold on a cold winter day. So not really the best option. So somewhere in the middle. we're looking in the middle, somewhere around the 0.35 range would probably be a good value for what we're doing. But again, it's very, directional specific. So is your house facing north? Where are all the windows facing? If the back of the house faces south and the house faces north, or conversely, they face the opposite direction, that can make a big difference. Give you an example, doing energy modeling for builders. We have one particular large builder, and they do a building or a house that sits on a corner lot. And when that corner lot house faces west, they rate 25% better than building code values when they do a performance model as opposed to the reference house. When we take that house and put it across the street so it faces east, it's actually below code values by 10%. So it makes a huge difference, and it's all solar heat gain. The U value makes a little bit of difference, but the solar heat gain makes a huge difference. So in terms of comfort, in terms of safety, things like peak cooling loads, if you have a lot of higher loaded windows in 0.7 range, it's going to be very hard to meet that peak cooling load maximum. And the peak cooling load is a calculation done. So if you're doing a Hot 2000 file and you're doing either code compliance or you're doing EnerGuide or Energy Star or whatever compliance path you're taking, after you model the house and you put the solar heat gain and the U values of the windows in there, what you'll get in the reports that are printed out in Hot 2000 is you'll get the peak cooling loads, depending on if you do it in BTUs or if you do it in kilowatts, you'll get the peak cooling loads for the performance house or the proposed house, and then you'll get the peak cooling loads for the reference house. So you'll see both of those, and you have to be at or below the peak cooling loads. And when that gets challenging is when you're doing multifamilies where you have one face with windows, and that's the only face. So it's got multifamily units on each side and one on the back. So the only face is the one that matters, and that's the calculation that's really going to mess you up. So those are the two main things that you want to consider when it comes to windows. The other ones here are important, but not nearly as important. So if you're looking at air leakage, that's going to affect things like how robust that window is in stormy weather, how it resists rain, how it performs when you're doing air tightness testing on the building and things like that. And then the other important one down here at the bottom is visible transmittance. The visible transmittance is the amount of natural light that comes through there. And you would think that the visible transmittance at 0.49 would be a really dark window. But realistically, it really, unless you put two windows side by side, it's very hard to tell that the visible transmittance is at 0.49. So that's a value when you look at the range, it's between 0 and 1. So a 0.49 is kind of, you've cut off 50% of the light. So, which isn't always a bad thing, but that needs to be considered when you're doing your design. So as you're doing design work, you look at the U value, you look at the solar heat gain, you look at the air leakage, and then you look at the visible transmissivity. And that tells you how much natural light comes in. And that gives you an overall value of the window. The other component you often see on window labels is the ER rating or the energy rating. Now, when the first building code came out with the energy code back in about 2017, we used to have window companies sending us the energy rating. And if you get the energy rating, that gives you a good value. So, for a current window in climate zone 7, I believe it's around 25. It has to be at least 25. Or prescriptively, it has to be 1.6 for a U value. And now we have the solar heat gains included in there as well. But the energy rating is actually a combination of U value, solar heat gain, and air leakage all put together. And it comes up with the energy rating. Now, the energy rating's fine, and you can use that in your designs. The problem is if you're doing energy modeling where you have to run it through Hot 2000 or use a specific software, you need the actual U value, solar heat gain, and air leakage to put into the software. You can't just use the energy rating. So those are the things to be mindful of when we're looking at designing windows. And they can have a big impact on how that house performs. Now, when it comes to the U value and how we calculate it, just a quick, simple formula here, we're multiplying it by 5.678. But if I take an average window, which is 1.6 U, and you notice here I use the USI value, so it's metric. This one is not the USI here. This should not be, just a U. So 1.6, if I convert that to RSI, I'm just taking 1 divided by 1.6, which gives me 6.25. And you notice that the watts moves from the front of the equation to the back of the equation. So if you're looking at a window and you're saying, it's 0.625, don't confuse that with, this number down here, the imperial U value. Make sure that the reference is an RSI. And then that gives you the value as a 1.6 or an RSI of 0.625. If I wanted to convert this exact window, right, down to a U value, again, the multiplier is here. And if I'm a person that just uses R value as an understanding, I could convert this back so that I could understand that a 1.6 window is actually an R value of 3.55. So now you start looking at the overall window design and you say, okay, here's a wall, and I put a window in that wall, and I know that that wall has a certain amount of studs in it. So there's about 23% of the wall that's stud, and there's 77% of the wall that's R19. Then I can get the effective value of the studs and insulation, which is typically around R13.5, give or take. Then I add in the window, which is 3.5. What's the best bang for my buck if I want to upgrade this whole assembly, including the window? Well, it's not to put insulation on the exterior of the wall. The best bang for my buck is to increase this window. So if I take this 1.6 and I drop it to a 1.0, that means the R value, which is in the inverse, goes up. So this is a 5.2 something something. So it's just converting it so that I can understand the language that's being used, so that I can understand what the effective values of my overall design are going to be in this environment. So which materials should I use and how should I use them? Well, when we talk about low E is the coatings that go on the window. And they're basically a silver coating that's microscopically applied in either a single, double, or triple layer. And as we put them into the multiple layers, we get either better blockage or we let more heat in. So a low solar heat gain window will have 3 layers of silver coating, blocks heat nicely. A single layer or a high solar gain window will have lots of heat in. So in the wintertime, exposed to the sun, I'm going to get lots of heat. Or I can do a medium solar heat gain where I'm balanced. And here's the numbers down below. So we have, solar heat gains. Here's the medium one, 0.55 to 0.35. It's a single layer. It's good for mixed climates. And the visible transmittance of the light, the natural light that comes in, is still reasonably good. So we can use a table like this, which is available on a lot of different window manufacturer sites, to understand what to use and how to use it. And we just really need to understand what is being done with the various layers and where the coatings are going. So here's how it works. When we look at windows, we always count the layers from the outside to the inside. So there's 2 faces to every piece of glazing. So we have layer 1 and 2 in the first piece on a triple glaze. We have layer 3 and 4 on the second, layer 5 and 6 on the third. In a double glaze, we only have 4 faces. But when I look at this window, for instance, and I go, okay, so this window is got a high solar heat E on the inside face on surface 3. It gives me a U value of 1.48, and it gives me a solar heat gain value. Let me see, I blocked that. It gives me a solar heat gain value of 0.68. So it's letting a lot of heat in. It's letting a lot of natural light in. And the U value is not too bad because it's got a high solar heat. So it's got 3 coatings of silver on the inside one face. Now, if I add 1 coating on the inside face of this window, but I use a low solar on this surface and a low solar on the inside surface, that gives me a better U value. But look at what it does to the solar heat gain here. It helps improve the solar heat gain significantly. So now I'm down to a 0.27. So if that's in a huge bank of windows on the back of a south-facing walkout building, this might be the way to go because I have enormous amount of windows and I have, at nighttime, I have better R value or better U value. So it gives me a better solution So I can design those windows specifically to the site, the amount of glass, to the amount of fenestration window to door ratio that I'm putting in there. If I go to a triple glaze window, it's the same principle, but here I've got low solar on one coating, right? 1.03 with a 0.25 solar heat gain. But look at what happens when I mix this and I go low solar heat gain outside, high solar gain inside, and then an interior solar low E coating as well on the inside. And now my R value or my U value has dropped to 0.64. That's a fantastic window. That's the best commercially available window that you can get on the market. And I don't believe it's available in Canada. It's just super impressive as a commercially viable window. So, but it's still only got a 0.24 in terms of solar heat gain. But you notice that the visible transmittant drops a little bit, but not a ton. So those are the ways that we look at windows, and we look at the U value, we look at the visible transmittance, and we look at the solar heat gain. And that helps us to understand, what windows we want to put in what location. So now we've designed the windows and we've determined that the window needs to go in a specific location. Now it comes time to install the windows. So one of the things that we don't often think about is the windows themselves are part of a plane of protection that the building code defines into two parts. We have what we call the first plane of protection and the second plane of protection. So when we look at the two planes of protection, the windows themselves are part of the first plane of protection, along with the cladding and along with the sealants that we use to seal the cladding to the windows. Now, a lot of people don't seal their windows, and a lot of enforcement is not there in the building code, even though the building code requires the windows to be sealed to the cladding. And that's particularly important on low drainage claddings like stucco and stone. Those materials, and when I say stone, I mean manufactured stone adhered like thick stucco. So if you're dealing with natural stone or a material that has very good drainage behind it, then it's not as important to have that sealant there. But for low draining materials, very important to have that caulking or sealant there. But this is first plane of protection. Now, the second plane of protection is the weather barrier. And the weather barrier is made up of your house wrap or your tar paper. It's made up of the membranes that you put around the window, but it's also made up of the flashings that will intersect and collect water as it's coming off of this layer and kick it away from the building. It's the same thing at the top of a window. As the water's coming down from the upper areas of the wall, we have a flashing over a window, both to deflect the water that's in front from the siding, but also to collect the water that's on the second plane and kick it out and away from that surface. So where we get a lot of failures in windows is we end up with too much moisture running down behind the materials. And then at the head of the materials, right here, it can't get out. Classic example of that is either a stone material or a stucco material with a hybrid acrylic finish. And what happens at the head of that window is there's no drainage capacity because they put the flashing on to the wall, they put the tar paper down over, and they put the wire and the scratch coat, and then they take the acrylic coating and they put it right down tight to the flashing. And then all the water that gets behind here has no way to exit and drain out. So those are important aspects of the window to understand when it comes to the installation methods that we use when we're putting the windows in. Now, the building code directs us down to the CSA 440. And that's the standard that helps us to understand how to install the windows. And that standard was written originally back in the late 90s. It's been updated a few times. In the last building code cycle, we used the 2007 version. And now we're using the 2019 version. So that version, I'm going to give you a way to link into that. There is an online tool that CSA has produced to help us to install windows to meet that standard. But that standard is the details on how to install a window. So first plane of protection, exterior cladding, second plane of protection, weather barrier, but more importantly is these flashings that are there and the sills of the rough opening that are there. So if you have a typical wall and you install a window into this opening back here, and you don't protect the sides or particularly the base of the window, it's susceptible to water getting into the rough opening. A lot of people feel that the window should be sealed so that water can't get in, but water is always going to get back there. So once the water gets in, what happens when it's sitting on this surface right here and it's got nowhere to go? It just tends to sit there and soak in and deteriorate that sill. So we need to look at the sills in this application to make sure that we're protecting them from incidental moisture that gets into that opening so that we can make sure that we can get rid of it so it doesn't build up and cause deterioration. Now, what better way to learn than learn from a principle that we already understand? So when we look at pressure planes and drainage planes, we have a classic example here of a vehicle, right? We don't put tape on the outside of the door to stop water getting into that opening right here. As we're driving down the road, the wind blows across this surface and the wind goes into that opening and it creates a pressure that's equal to the outside air. So if there's no pressure differential, there's no suction. And so as you drive down the road, there's very little water and liquid that actually makes it into that opening where the weather seal is located. So the weather seal is not subjected to a high volume of water. It's subjected to a very low volume of water because this is where the pressure drop occurs. There's a high pressure on the outside as the wind is blowing across the vehicle, and there's a high pressure in the cavity, but on the inside over here, there's a very low pressure. So if water comes in contact and the weather stripping isn't completely 100% in contact, then it creates a vacuum and sucks the water through. So we want to have the pressure differential out here, and we want to have the air seal away from where there's going to be large quantities of water in contact. So we can use this principle in design of windows in how we deal with windows and take care of moisture, especially in climates such as in Alberta where we get a lot of wind. So that means when we look at the design of a window, right, here's the rain coming down and there's the first plane of protection. The water drains off and drains away. But we also have this internal drainage system that most people aren't aware of, right? You always see this little weep right here on the front of the window that lets the water that gets into the window mechanism drain out. So that little drainage path gets rid of the water that could accumulate that gets in around these locations where the glass maybe isn't completely tight, or as the wind moves, it opens it up, or as the seals start to break down, water gets in there, and that drains the water out. But we want to replicate that in the rough opening. So right here in this particular rough opening, we want this to be a collection point for incidental water. We're not going to have a lot there, but we're going to have some there. And when water gets into that location, how do we get it out? Well, we can put a back dam here, or we can put a slope on this. And when we do that, we also put an air barrier right here so that we have a continuous air block. So it's just like that car door where we have air and wind blowing at it here. So this is a high pressure. We have a high pressure in here because we let lots of wind and air back into this cavity. And then the drainage or the pressure plane and the air barrier right back here is never going to be in contact with very much moisture. So then when we do get moisture into that cavity, we can effectively drain it back out. Now, this isn't something that we've just dreamed up. This was a 5-year study that CMHC and NRC put together, followed by a 2-year study that questioned, should we put insulation in this cavity? And the answer is no. And the reason the answer is no is because we don't insulate this cavity or this cavity or this cavity, but we compartmentalize them. We don't just make a window with one giant cavity. We compartmentalize those because the convective looping here effectively gives us insulation against this cavity, against this cavity. So we get the same principle down here by putting an air seal here and making sure that it's continuous. So if we were to look at the drainage and the air seal locations here, this helps us to understand where we want the pressure plane where we're separating high pressure from low pressure. So we have a high pressure on the right, and inside the house where there's no wind, we have a low pressure on the left. Well, look at the green line, the dotted line that goes all the way through. So we intercept the window, which goes to a piece of rubber seal here, which goes to a piece of vinyl, which goes down to another bit of caulking. We've got the membrane sealing, which intersects with the OSB, which intersects with a rough opening of the 2x6, and continues on with a bead of caulking, acoustical, down to the poly that goes on the inside. So we've created this continuous air barrier all the way through. And if we get that air barrier reasonably tight, and if water can't touch that air barrier, we're not going to get suction through. So if I have a little opening here, or I have a little opening here, or I have a little opening here, there's no water in contact with it to get it sucked in. And because everywhere there's these openings, I've also protected these surfaces. So right here, instead of putting a house wrap or putting nothing, I've put a water impermeable material that can protect the water from coming out at those locations. So does it work? Well, let's look at an example here. This is a video of a water test. So in this water test, we put a blower door into the house. We simulate a high wind doing that. So we create a low pressure in the house compared to outside, and we spray water. We tape off the windows and the window connections to the glass. Now look at where the water is exiting. So this has a drainage plane behind the stucco, and the water is exiting wherever it finds a place to leave. The weak point in this assembly is look at the head of the windows. Actually, look at the bottom of the windows right here. See, what we see there is that the drain plane of the bottom of the window is working very well, but there is nowhere to get rid of the water that's building up on the head of the window. So the head of the window is the weak point and the cause of this window. This was a perfect installation other than the head of the window not releasing the water that was building up in behind here. And then what would happen is, because of the volume of water getting in, because there was no sealant or caulking on the sides of these windows or the bottom of the windows, the water that was building up in behind here would come down to the window head and try and escape, and it couldn't. So it'd build up a hydrostatic head pressure. And if you had 4 or 5 inches of water building up on this surface, 4 or 5 inches of head pressure, we know that 1 inch of water column is equal to 250 pascals. So multiply that by 4, and it gives you an idea of the hydrostatic pressure that's building up behind there. So it forces the water up and around the flashing head, which is only 2 inches, and then it forces it through any staple holes that you have at that location. And then the window leaks, even though there was a really good, robust drainage plane behind this stucco. So it's a really good illustration of wind-driven rain and how wind can be our friend, but it's the entry and the exit. It's achieving a moisture balance. So if I'm letting X amount of water in, I better let equal to or more than that escape when it gets to the flashings, which are part of the second plane of protection. Here's another example. This example is of a window that was installed below vinyl siding, and the window itself had a flashing at the head, but not at the bottom. So when you look at the destruction that was done here, they sealed the window into place. They put the window in place. Let's just go back for a second here. Here's the entry point of the water, right? There's no caulking at that location. So when water gets in there, it comes down and it runs down to this surface. But because there's no drainage all the way through this whole assembly, and you can see the efflorescence on the stone, which is part of the indication that there's something going on there. It's never drying out. But because the water was entering here, let me get rid of these lines for a second, carry on with the video. And it was entering there, whoops, let's go back. It was not cooperating. It was entering there all the way up at the multiple windows that were above it. It was putting way more water in behind onto the second plane of the drainage plane than it was letting escape. And so the water just sat there and soaked through all the materials and all the assembly and rotted out the OSB wall. So watch what happens when we look up. There's that entry point there, but we have the same entry point on the upper windows there. And we're going to get way more entry right here at the bottom of these windows. and then because of the vinyl, it drains down and it comes around the windows, and there's no sealant here to protect water from getting in there. So the entry points for this was here, was at the bottom of the windows, was at the sides, all the way down, and the water couldn't get out as fast as it was getting in. So this was a 7-year-old deteriorated structure. Here's an EIFS system, and this particular system is, let's kill the sound here. This particular system has been sealed in place. So these are flanged windows, but look at how much water gets trapped behind here. Right, so we've trapped all the water in behind this assembly, and now it can't get out. So every time water gets in around this building or this connection, it's got nowhere to go. Now, fortunately, in this application, they put a batten board all the way around it to trim it out. But it just gives us an indication of, you know, when water gets in, how does it get out? And on this third video, this is a really well done application, except there's no sill protection. And the entry point was not the window. The entry point was above the window. It was wind-driven rain getting into the soffitting and getting behind the house wrap, running down, getting into the head of the window, running around the rough opening, and then collecting at the bottom. And there was nothing protecting that sill. So everything behind there was deteriorated. And this is a 3-year-old house. So you're seeing these deteriorations and these damages occurring very early in the process. And what's sad about this is this particular builder and the homeowner went to a lot of trouble to use, they used fir plywood. They got a hold of, they didn't want to use OSB. They didn't want to use any, engineered products. They went with real wood, simply because they were worried about the deterioration that could occur on OSB and other types of manufactured lumber. And yet they didn't think of the most important part, which was the rough opening of the sill. Now, doors, we don't talk about doors very often, but here's an example of a door, the way we used to install doors, and hopefully no one is installing this way anymore with a face seal. But if you look at this door, this is on a deck on a multifamily site, so there's like 152 units here, and they've installed the doors this way. This is during construction. And when you point this out, they're like, well, this is the way we've always done it, right? We put the door in, we don't put any protection in the door, and then we put the vinyl up and around it, and we put this nice big heavy bead of sealant all the way around. Well, what does the sealant do? Well, let's look at the way a door is designed. Here's the upper part of the door, and here is the entry point, because here's the weather stripping. So it's an outswing door. So you close the door, the wind blows through, and if there's any kind of airflow possible through here, the wind and the water flow through into these two openings here, and now it's in there. And now, because of the way you've installed it, you've sealed it to prevent anything that got in there from getting out. We also have penetrations here that eventually break down, which are behind the plane of where this surface is going to be. So we're letting moisture get in there. And here's the outcome. Like, sometimes I guess we need to scare ourselves. This was a factor of the window not having sill protection. This was another factor of a stucco application where there was no drainage at the head of the windows. Now, they put the windows in and they sealed everything really well, but there was no way for water to get out of the building. So they were letting a lot of water enter in. It got into the rough openings. There was no sealant from the window to the stucco. And the entry point was letting way more water that could get in than could get out. And even though the windows were sealed in place, the entry was not the windows. The entry is other locations. So when we look at something like this, and we take a building apart that is only 6 years old, it's still just, right? The OSB is black, it's saturated, and this is a 6-year-old building that has been exposed to too much wind and rain. And the OSB is just disintegrated and gone. So, nice house on the lake, $2.5 million house that has to be completely rebuilt at the back. Some of it was structural, some of it was just the OSB that had to be replaced. So it just gives us an example of how dangerous it can be if we don't properly install the windows. And what we have in a lot of cases is we have individuals that want to seal the outside face of the windows, and they say, well, water shouldn't get in there in the first place. That's not the question. The issue is the water that gets in from an upper source. This is a water test that you're looking at here. The water was getting in at a roof connection above this roof, above this door at the front entry. And as the water got in above the roof connection, it ran down, it got behind the house wrap and ended up inside and was leaking in the window. So, it's caused by wind and rain. It pushes water and air where you wouldn't think it would push it, and it gets in there, creates these kind of challenges for us. If there's a living room window in another situation where the water was getting in from the upper window, and it was nothing to do with the window itself. It was the fact that at the bottom of the window, where the cladding met the window, there was no caulking. So the water was entering at that point, running down and leaking out at the window below it. So these are just some examples. So when we look at windows, these are critical details here, right? There's a couple of important components here that we need to understand. First of all, we have a giant heavy piece of glass. We need to support this vinyl window with a good, heavy, non-absorbent block. So piece of plastic, piece of treated lumber, something that's not going to absorb water and swell and change dimensional shape. So that's very important. We also want to make sure that we protect this surface up to the line of where the window ends. This jamb extension is not part of the window. It's an interior connection. But if we have a window design like this, where the jamb extension gets installed early in the process, it comes from the manufacturer, then this has to be continuous, one piece. So it has to be sealed right here so that the air can't get through. Because if we seal it here and the air can get through here, we'll have a problem. And it's the air. There's two parts to this. There's the air that gets in that creates the condensation sitting on a flat surface, but there's also the air that blows through here. And if it can blow through and there's rainwater in contact with it, it's going to pull that rainwater into that opening as well. So the simple process here is, put a back dam on, put something to block it. That could be a backer rod with caulking. That could be a piece of wood. That could be a slope sill. There's some fantastic manufactured slope sill products on the marketplace that can help do that. But it's getting the water out of the opening. But then it's also, when you look at the jambs, here's the exterior here. So there's the vinyl siding. It's also taking water that gets into these areas here that gravity is going to pull down and dealing with those. So something more drainable and more resistant to moisture, like a hygroscopic mineral wool, is going to perform better because the water will drain through it. It won't get trapped. And if the water gets into this material and gets trapped, do we have a piece of material here that's going to resist the absorption of the water to get through there until it can evaporate, or till water, the gravity takes it down to the bottom and gets rid of it. So if we look at the location of the air seal, right, we've got this piece of rubberized material joining the back dam to the window, and then we've got a good backer rod here sealing it off as well, but we've maintained the drainage path here. So these are some of the things that CSA A440 Window Installation Guide walks us through. Now, one of the things
we just have about
about
5 more minutes, Darrell. I just wanted to give you a heads up in interest of time. We can stay on after and answer some questions, but 5 more minutes.
Yep. Okay, sounds good. So we are pretty much done. So in terms of drainage, one of the reasons why when you take spray foam in an open cell format and we blow it into the window rough openings, here's what happens to spray foam when it's in contact with water too much. Right? It just simply absorbs the moisture. So this is an open cell. This is a can type foam. If you take the foams, the modern foams now, and you spray them into the opening, as long as you don't cut the surface, they remain water resistant. But if you cut the surface, they are open to absorbing water into them. And so that's one of the dangers. If you don't protect that rough opening and you put spray foam in there, you cut it to trim the window out, and then moisture gets in there, then that can create some problems for you. So here's where some of the entry points come. So, you look at a detail like this. If this doesn't get overlapped over the next layer, or if this joint doesn't get protected, there's the entry point from above, and it gets into the joint right here at the OSB. And once it's into the joint of the OSB, it just trickles down and gets into the rough opening. even though you've sealed that flange to the window. So the window is sealed to that flange. It's too late. You haven't protected it up here. So that means that that water that gets in there needs a place to go and drain to the bottom. There is a book, Building Envelope Tie-in Details, which walks you through all of these details that's available online through the Siding Contractors Association of Alberta. And that book actually walks you through all these details are taken out of that book, or a lot of these details are taken out of that book. So when you look at the details such as this, you're allowing the water that could get in here to drain into this drainage cavity. You've still got your insulation, you've still got your air barrier, but then it can flow down and through the assembly into the sill where it's directed back outside. So one of the really good resources that's available online, and here's the QR code. If you want to snap a shot of this QR code, this is a fantastic online tool provided by CSA. You can get your copy of the standard there if you want to shell out the cash, or you could just use this and you can pick up the information there on why it's important to install windows a certain way as per the CSA standard. And then they will give you the breakdown in 3 steps, part 1, part 2, part 3, on how to install windows to meet the CSA standard without having to buy the standard. And not only does it cover flanged windows, but it covers box non-flanged windows as well. So that's a really good resource for looking at in terms of, how do we install a window correctly? Does my method that I want to use meet the standard, the principles that are located in the standard? Because there's probably 20 ways to install it right, just as much as there's 20 ways to install it wrong. So this is a really good resource to keep in mind. So last thoughts, don't detail your windows this way, first of all. But if you simply treat the windows and doors as porous, if you protect the rough opening and particularly the sill, if you drain the rough opening, ignore that number 2, and ignore that number, I don't know what that's doing. If you put the air tightness at the interface where the interface of the air barrier meets the interface of the jamb extension on the interior, and then structurally support the glass, then you'll be able to have a very effective window in terms of the installation process. So that is the end of the information I wanted to share with you. Is there any questions?
I don't see any that came into the chat, so thanks to everyone for attending our session today, and thanks to Darrell for presenting, and to SSRIA and ENBIX for organizing. Please let us know what you think, and just a reminder to check out our buildings for our ENBIX calendar for upcoming events, and we can stay on for a few minutes if there's any additional questions. Thanks, everybody. Have a great day.